underground lie hidden stores of petroleum. Sometimes they reveal their presence on the surface. Long ago, primitive man collected it for use as a medicine. But the white man found other uses for it and began drilling for oil about 100 years ago. Of course, at first it was very much a matter of luck. One borehole would tap new wells at 60 feet, while not far away the unlucky ones failed to find it. Now, millions of years ago, all this was under the sea. And on the seabed, vast layers of mud were being compressed into rock. In the rock, tiny particles of oil were formed from the bodies of minute living creatures. Above them, various other rock formations were made. Some were porous, some were not. When a porous strata was capped by a watertight rock, the oil being formed floated up until it could go no further. Now, Earth movement slowly folded these flat layers of rock and thrust them up above the sea. Sometimes a trap was formed where the oil could collect. And if a crack allowed a trickle of oil to escape to the surface, the presence of the hidden reservoir was revealed. One well, sighted at random, might strike lucky. Or it might not. Another might produce unlimited quantities of salt water, so the wells crowded all round the lucky strike. And no one could say how long the luck would last. For all they knew, there might be other supplies near at hand which didn't show on the surface. Now here's a much larger reservoir, an anticline. The oil is trapped at the crest of a gentle fold. You know, in some parts of the world, the earth crust has been folded much more severely. Now, much of the original surface has been worn away by wind and weather, and what remains will give a clue to the shape of things below. Unless, like this, the top layers have shifted further forward. You see, in this case, no seepages betray the presence of oil in the anticline. Over here is a dead oil field, that allowed the oil to escape. But even today, traces of the long-departed oil remain to encourage the geologist to search for other reservoirs nearby. And since he cannot see the shape of the formations which lie beneath his feet, he must deduce their existence by what he sees on the surface. Here's the kind of porous rock that oil would collect in. Smells interesting. I wonder if there's a cap rock. Yes, that's it all right. Now, what about the other side? Here it is. And it dips in that direction. Yes, that bed of porous and fissured rock probably stretches underground for miles. So I'll have to search for another fold over there. It'll save time if I take a look from the air. That's where I was, down there. The strike was roughly north and south, and the cap rock dipped down in that direction. So somewhere over here I may find another fold running north and south. This looks promising. Now, if those two outcrops turn out to be part of the same original strata, there may be an oil-bearing anticline between them. I must go down and make sure. Yes, they're the same all right. There's pretty clear evidence of a fold here. So if the folding is not displaced, there should be an oil-bearing anticline about here. If the anticline is where I think it is, the best position for the well would be here, just below the crest on the steeper flank. Yes, but if I'm wrong, the borehole might strike gas which may have gathered on the top of the oil. or it may strike the water the oil's floating on. This is where I must wait for the geophysicist to check my estimate. A charge exploding 100 feet below the surface sends out shock waves in all directions. When they reach a different formation, they're reflected back towards the surface. In the meantime, some of the waves have gone direct to the surface and are picked up by a listening device called a geophone. The reflected waves arrive later. The difference between the time taken by the direct waves and the reflected waves to arrive at each geophone is recorded in the listening truck in the form of a chart. The charts from a series of explosions enable the geophysicist to plot the shape of the underground formation. So it turns out, after all, that in this region the underground folds don't conform with the surface. Now we know where we are. And the point on the endocrine to aim for is here. The geophysical survey has also shown me the positions of the intermediate beds. So now I can give the driller a chart of the key horizons which lie between him and his target.
This is going to be a full-sized job. First, we'll have to build a road to bring more than 1,000 tons of equipment onto the site. Then we have to get the derrick up. That's over 100 feet high. Then come drill pipe, drilling machinery, pumps, engines, tools, well casing, tons and tons of cement, chemicals, mud tanks, and a good supply of water. According to the geologist, we've got to go down 7,000 feet to this formation, where we hope to find oil. Above that is the cap rock, sealing it in under very high pressure. And here's a very convenient bed of shelly limestone, which the geologist can easily recognize when we get to it. We'll use this as our marker bed to tell us when we're nearly through to the imprisoned oil. Here are more key horizons he's going to recognize on the way down. Water here, probably, which will need sealing off. And here's the bed of very hard rock we're drilling now. 12-inch rock bit, and making progress at about 4 feet an hour. The drill stem is made up of hollow tubes, down which a stream of mud slurry is pumped, passing out through nozzles in the bit, and returning up the space outside the drill stem, carrying the cuttings from the bit up to the surface. This drilling mud is made up of suitable clays and chemicals. It seals off the sides of the hole and helps to lubricate the bit and keep it cool. Immediately above the bit are several heavy tubes which give weight to the bit and help to keep the hole straight. Above that, many lengths of drill pipe are jointed together. At 250 feet or so below the surface, the anchor string of steel casing to line the first part of the hole has already been cemented in from top to bottom. And wellhead control fittings are bolted to the casing. On the derrick floor is our rotary table. Through it passes the topmost length of the drill stem, a square section pipe called the Kelly. The Kelly is gripped in a square drive bushing in the revolving table, through which it slides down freely as the hole gets deeper. The upper end of the Kelly revolves on a swivel. The weight of the string is taken through the swivel to a hook on the travelling block and to the crown block on the derrick head. The strong steel cable from the block leads to the drum of the drawworks, where the driller can feed out to control the weight on the bit as it progresses. The The supply of drilling mud is mixed in tanks to the required gravity and pumped along to the derrick, where a flexible hose takes it to the swivel and so down through the kelly and the drill pipe to the bit far below.
On its return to the surface, the mud, loaded with cuttings, is taken by way of the conductor box and flow lines to vibrating screens. Take out the cuttings and return the mud to be examined by the geologist through his microscope, and provide him with a complete record of all the different rocks the drillers passed through.
When the kelly can go no further, time to insert another 30-foot legal pipe. So we must stop now and hoist the kelly clear of the table. Then off we go again, stopping to add a new length of pipe every 30 feet through. All the time the driller is on the alert, ready to take action if his indicators and the feel of his controls tell him of any change in the situation down below. And the geologist, examining the cuttings of each different sort of rock as the bit passes through it, can often give warning of possible difficulties ahead. Now we've got to that waterlogged formation. Extra water isn't going to do our mud column and the walls of the hole any good, so we'll have to seal it off with another string of casing as soon as we've got through it. We pull out the drill string and they strike oil under pressure before we're quite ready. The master bed will tell us when we're getting dangerously close. Here we need a special bit with a hollow center, which brings up a complete cylindrical core from the center of the hole. The geologist knows that a certain type of fossil is found only in this particular bed. Recognizes these in his microscope. We know it's time to set our last string of casing, the production string. From here on, we must go very carefully. Now we must examine samples continuously until we know we're into the porous rock we're looking for. We're depending on the weight of the column of mud in the hole to control the pressure we expect to find in the oil formation. And if too much mud leaks out to the formation on the way, we must be ready to replace it at once and keep the hole full, or the well may blow out in us, and that would be serious. Each time we bring up a core, thousands of feet of drill pipe must be pulled to bring the core barrel to surface.
It's a nice, juicy-looking core of limestone. Chip from this in a test tube. A drop of chloroform will show if there's oil there or not. And there it is. We've only to drill a few feet more to make the well good enough for production. Then the driller can take his rig away to another prospect, and all that remains is to connect up and pipe the newfound oil away wherever it's wanted.